Chapter 3. Greece. Enormous economic and political changes occurred in and around the Mediterranean basin during the last centuries of the second millennium. In a turbulent atmosphere of migrations and wars, the Bronze Age was replaced by what has been called our age, the Age of Iron. Few details are known about this period of revolutions, but we find that towards its end, perhaps around 900 BC, the Minoan and Hittite empires had disappeared. The power of Egypt and Babylonia had been greatly reduced, and new peoples had come into historical setting. The most outstanding of these new peoples were the Hebrews, the Assyrians, the Phoenicians, and the Greeks. The replacement of bronze by iron brought not only a change in warfare, but also increased the social surplus, stimulated trade, and allowed larger participation of the common people in matters of economy and public interest. This was reflected in two great innovations: the replacement of the clumsy script of the ancient Orient by the easy-to-learn alphabet, and the introduction of coined money, which helped to stimulate trade. The time had come when culture could no longer be the exclusive province of an Oriental officialdom. The activities of the sea raiders, as some of the migrating peoples are styled in Egyptian texts, were originally accompanied by great cultural losses. The Minoan civilization disappeared. Egyptian art declined. Babylonian and Egyptian science stagnated for centuries. No mathematical texts have come to us from this transition period, when stable relations were again established. The ancient Orient recovered mainly along traditional lines, but the stage was set for an entirely new type of civilization, the civilization of Greece. The towns that arose along the coast of Asia Minor and on the Greek mainland were no longer administration centers of an irrigation society. They were trading towns in which the old-time feudal landlords had to fight a losing battle with an independent, politically conscious merchant class. During the 7th and 6th centuries BC, this merchant class won ascendancy and had to fight its own battles with the small traders and artisans, the demos deiot. The result was the rise of the Greek polis, the self-governing city-state, a new social experiment entirely different from the early city-states of Sumer and other Oriental countries. The most important of these city-states developed in Ionia on the Anatolian coast. Their growing trade connected them with the shores of the whole Mediterranean, with Mesopotamia, Egypt, Scythia, and even with countries beyond. Miletus for a long time took a leading place. Cities on other shores also gained in wealth and importance. On the mainland of Greece, first Corinth, later Athens. On the Italian coast, Croton and Tarentum. In Sicily, Syracuse. This new social order created a new type of man. The merchant trader had never enjoyed so much independence. But he knew that this independence was a result of a constant and bitter struggle. The static outlook of the Orient could never be his. He lived in a period of geographical discoveries comparable only to those of 16th century Western Europe. He recognized no absolute monarch or power supposedly vested in a static deity. Moreover, he could enjoy a certain amount of leisure, the result of wealth and slave labor. He could philosophize about this world of his. The absence of any well-established religion led many inhabitants of these coastal towns into mysticism, but also stimulated its opposite, the growth of rationalism and the scientific outlook. Modern mathematics was born in this atmosphere of Ionian rationalism, the mathematics that not only asked the Oriental question how, but also the modern, scientific question why. The traditional father of Greek mathematics is the merchant Thales of Miletus, who visited Babylon and Egypt in the first half of the 6th century. Even if his whole figure is legendary, it stands for something eminently real. It symbolizes the circumstances under which the foundations not only of modern mathematics, but also of modern science and philosophy were established. The early Greek study of mathematics had one main goal: the understanding of man's place in the universe according to a rational scheme. Mathematics helped to find order in chaos, to arrange ideas in logical chains, to find fundamental principles. It was the most rational of all sciences. And though there is little doubt that the Greek merchants became acquainted with Oriental mathematics along their trade routes, they soon found out that the Orientals had left most of the rationalization undone. Why had the isosceles triangle two equal angles? Why was the area of a triangle equal to half that of a rectangle of equal base and altitude? These questions came naturally to men who asked similar questions concerning cosmology, biology, and physics. It is unfortunate that there are no primary sources which can give us a picture of the early development of Greek mathematics. The existing codices are from Christian and Arabic times, and they are only sparingly supplemented by Egyptian papyrus notes of a somewhat earlier date. Classical scholarship, however, has enabled us to restore the remaining texts, which date back to the 4th century BC and later, and we possess in this way reliable editions of Euclid, Archimedes, Apollonius, and other great mathematicians of antiquity. But these texts represent an already fully developed mathematical science, in which historical development is hard to trace even with the aid of later commentaries. For the formative years of Greek mathematics, we must rely entirely on small fragments transmitted by later authors and on scattered remarks by philosophers and other not strictly mathematical authors. Highly ingenious and patient text criticism has been able to elucidate many obscure points in this early history, and it is due to this work carried on by investigators such as Paul Tannery, T. L. Heath, H. G. Zuthan, E. Frank Godig, and others, that we are able to present something like a consistent, if largely hypothetical, picture of Greek mathematics in its formative years. In the 6th century BC, a new and vast oriental power arose on the ruins of the Assyrian Empire, the Persia of the Achaemenides. It conquered the Anatolian towns, but the social structure on the mainland of Greece was already too well established to suffer defeat. The Persian invasion was repelled in the historic battles of Marathon, Salamis, and Plataea. The main result of the Greek victory was the expansion and hegemony of Athens. Here, under Pericles in the second half of the 5th century, the democratic elements became increasingly influential. They were the driving force behind the economic and military expansion and made Athens by 430 not only the leader of a Greek empire, but also the center of a new and amazing civilization, the Golden Age of Greece. Within the framework of the social and political struggles, philosophers and teachers presented their theories, and with them the new mathematics. For the first time in history, a group of critical men, the sophists, less hampered by tradition than any previous group of learned persons, approached problems of a mathematical nature in the spirit of understanding rather than of utility, as this mental attitude enabled the sophists to reach toward the foundations of exact thinking itself. It would be highly instructive to follow their discussions. Unfortunately, only one complete mathematical fragment of this period is extant. It is written by the Ionian philosopher Hippocrates of Chios. This fragment represents a high degree of perfection in mathematical reasoning and deals, typically enough, with a curiously impractical but theoretically valuable subject, the so-called lunulae, the little moons or crescents bounded by two circular arcs. The subject, to find certain areas bounded by two circular arcs which can be expressed rationally in terms of the diameters, has a direct bearing on the problem of the quadrature of the circle, a central problem in Greek mathematics. In the analysis of his problem, Hippocrates showed that the mathematicians of the Golden Age of Greece had an ordered system of plane geometry, in which the principle of logical deduction from one statement to another had been fully accepted. A beginning of axiomatics had been made, as is indicated by the name of the book supposedly written by Hippocrates, the Elements Stoicheia, the title of all Greek axiomatic treatises, including that of Euclid. Hippocrates investigated the areas of plane figures bounded by straight lines as well as circular arcs, the areas of similar circular segments. He teaches are to each other as the squares of their chords. Pythagoras' theorem is known to him, and so is the corresponding inequality for non-rectangular triangles. The whole treatise is already in what might be called the Euclidean tradition, but it is older than Euclid by more than a century. The problem of the quadrature of the circle is one of the three famous mathematical problems of antiquity, which in this period began to be a subject of study. These problems were the trisection of the angle, that is, the problem of dividing a given angle into three equal parts, the duplication of the cube, that is, to find the side of a cube of which the volume is twice that of a given cube, the so-called Delic cube, the quadrature of the circle, that is, to find the square of an area equal to that of a given square. The importance of these problems lies in the fact that they cannot be geometrically solved by the construction of a finite number of straight lines and circles, except by approximation, and therefore they served as a means of penetration into new fields of mathematics. They led to the discovery of the conic sections, and some cubic and quartic curves, and to one transcendental curve, the quadratrix, the anecdotic forms, in which the problems have occasionally been transmitted, Delphic oracles, etc., should not prejudice us against their fundamental importance. It occurs not infrequently that a fundamental problem is presented in the form of an anecdote or a puzzle, Newton's apple, Cardan's broken promise, or Kepler's wine barrels. Mathematicians of different periods, including our own, have shown the connection between these Greek problems and the modern theory of equations, involving considerations concerning domains of rationality, algebraic numbers, and group theory, probably outside of the group of sophists, who were in some degree connected with the democratic movement, stood another group of mathematically inclined philosophers related to the aristocratic factions. They called themselves Pythagoreans after a rather mythical founder of the school, Pythagoras, supposedly a mystic, a scientist, and an aristocratic statesman, where most sophists emphasized the reality of change. The Pythagoreans stressed the study of the unchangeable elements in nature and society, in their search for the eternal laws of the universe. They studied geometry, arithmetic, astronomy, and music, the quadrivium. Their most outstanding leader was Archytas of Tarentum, who lived about 400, and to whose school, if we follow the hypothesis of Isch, Frank, Gorik, much of the Pythagorean brand of mathematics may be ascribed. Its arithmetic was a highly speculative science, which had little in common with the contemporary Babylonian computational technique. Numbers were divided into classes: odd, even times even, odd times odd, prime and composite, perfect, friendly, triangular, square, pentagonal, etc. Some of the most interesting results concern the triangular numbers, which represent a link between geometry and arithmetic. Our name square numbers had its origin in Pythagorean speculations. The figures themselves are much older, since some of them appear on Neolithic pottery. The Pythagoreans investigated their properties, adding their brand of number mysticism, and placing them in the center of a cosmic philosophy which tried to reduce all relations to number relations. Everything is number. A point was unity in position. The Pythagoreans knew some properties of regular polygons and regular bodies. They showed how the plane can be filled by means of patterns of regular triangles, squares or regular hexagons, and space by cubes, to which Aristotle later tried to add the wrong notion that space can be filled by regular tetrahedra. The Pythagoreans may have also known the regular octahedron and dodecahedron, the latter figure, because pyrite, found in Italy, crystallizes in dodecahedra, and models of such figures as ornaments or magical symbols date back to Etruscan times. As to Pythagoras' theorem, the Pythagoreans ascribed its discovery to their master, who was supposed to have sacrificed 100 oxen to the gods as a token of gratitude. We have seen that the theorem was already known in Hammurabi's Babylon, but the first general proof may very well have been obtained in the Pythagorean school. The most important discovery ascribed to the Pythagoreans was the discovery of the irrational by means of incommensurable line segments. This discovery may have been the result of their interest in the geometric mean. What was the geometric mean of 1 and 2? Two sacred symbols. This led to the study of the ratio of the side and the diagonal of a square, and it was found that this ratio could not be expressed by what we now call rational numbers, the only numbers recognized as such. This discovery, which upset the easy harmony between arithmetic and geometry, was probably made in the last decades of the 5th century BC. It came on top of another difficulty, which had emerged from the arguments concerning the reality of change, arguments which have kept philosophers busy from then until the present. This difficulty has been ascribed to Zeno of Elea, around 450 BC, a pupil of Parmenides, a conservative philosopher who taught that reason only recognizes absolute being, and that change is only apparent. It received mathematical significance when infinite processes had to be studied in such questions as the determination of the volume of a pyramid. Here Zeno's paradoxes came in conflict with some ancient and intuitive conceptions concerning the infinitely small and the infinitely large. It was always believed that the sum of an infinite number of quantities can be made as large as we like. Even if each quantity is extremely small, and also that the sum of a finite or infinite number of quantities of dimension 0 is 0. Zeno's criticism challenged these conceptions, and his four paradoxes created a stir of which the ripples can be observed today. They have been preserved by Aristotle and are known as the Achilles, the arrow, the dichotomy, and the stadium. They are phrased so as to stress contradictions in the conception of motion and of time. No attempt is made to solve the contradictions. The gist of the reasoning will be clear from the Achilles and the dichotomy, which we explain in our own words as follows. Achilles. Achilles and a tortoise move in the same direction on a straight line. Achilles is much faster than the tortoise. But in order to reach the tortoise, he must first pass the point P from which the tortoise started. If he comes to P-ha, the tortoise has advanced to point Pone. Achilles cannot reach the tortoise until he passes Pone. But the tortoise has advanced to a new point P2. If Achilles is at P2 Pore, the tortoise has reached a new point P3, etc. Hence Achilles can never reach the tortoise. Dichotomy. Suppose I like to go from A to B along a line. In order to reach B, I must first traverse half the distance AB, and in order to reach halfway, I must first reach the halfway point between A and Bone. This goes on indefinitely, so that the motion can never even begin. Zeno's arguments showed that a finite segment can be broken up into an infinite number of small segments, each of finite length. They also showed that there is a difficulty in explaining what we mean by saying that a line is composed of points. It is very likely that Zeno himself had no idea of the mathematical implications of his arguments. Problems leading to his paradoxes have regularly appeared in the course of philosophical and theological discussions. We recognize them as problems concerning the relation of the potentially and the actually infinite. Paul Tannery, however, believed that Zeno's arguments were particularly directed against the Pythagorean idea of space as the sum of points. Whatever the truth may be, Zeno's reasoning certainly influenced mathematical thought for many generations. His paradoxes may be compared to those used by Bishop Berkeley in 1734, when he showed the logical absurdities to which poor formulation of the principles of calculus may lead, but without offering a better foundation himself. Zeno's arguments began to worry the mathematicians even more after the irrational had been discovered. Was mathematics as an exact science possible? Tannery has suggested that we may speak of a veritable logical scandal, of a crisis in Greek mathematics. If this is the case, then this crisis originated in the later period of the Peloponnesian War, ending with the fall of Athens in 404 BC. We may then detect a connection between the crisis in mathematics and that of the social system, since the fall of Athens spelled the doom of the empire of a slave-owning democracy, and introduced a new period of aristocratic supremacy, a crisis that was solved in the spirit of the new period. Typical of this new period in Greek history was the increasing wealth of certain sections of the ruling classes, combined with equally increased misery and insecurity of the poor. The ruling classes based their material existence more and more upon slavery, which allowed them leisure to cultivate arts and sciences, but made them also more and more averse to all manual work. A gentleman of leisure looked down upon work which slaves and craftsmen did and sought relief from worry in the study of philosophy and of personal ethics. Plato and Aristotle expressed this attitude, and it is in Plato's Republic, written perhaps around 360, that we find the clearest expression of the ideals of the slave-owning aristocracy. The guards of Plato's Republic must study the quadrivium, consisting of arithmetic, geometry, astronomy, and music, in order to understand the laws of the universe. Such an intellectual atmosphere was conducive, at any rate in its earlier period, to a discussion of the foundations of mathematics and to speculative cosmogony. At least three great mathematicians of this period were connected with Plato's academy, namely, Archytas, Theaetetus, died 369, and Eudoxus, circa 408-355. Theaetetus has been credited with the theory of irrationals as it appears in the 10th book of Euclid's Elements. Eudoxus' name is connected with the theory of proportions which Euclid gave in his 5th book, and also with the so-called exhaustion method, which allowed a rigorous treatment of area and volume computations. This means that it was Eudoxus who solved the crisis in Greek mathematics, and whose rigorous formulations helped to decide the course of Greek axiomatics and, to a considerable extent, of Greek mathematics as a whole. Eudoxus' theory of proportions did away with the arithmetical theory of the Pythagoreans. which applied to commensurable quantities only. It was a purely geometrical theory, which in strictly axiomatic form made all reference to incommensurable or commensurable magnitudes superfluous. Typical is definition 5. Book 5 of Euclid's Elements. Magnitudes are said to be in the same ratio, the first to the second and the third to the fourth, when, if any equimultiples whatever be taken of the first and third, and any equimultiples whatever of the second and fourth, the former equimultiples alike exceed, are alike equal to, or are alike less than, the latter equimultiples taken in corresponding order. The present theory of irrational numbers, developed by Dedekind and Weierstrass, follows Eudoxus' mode of thought, almost literally, but by using modern arithmetical methods, has opened far wider perspectives. The exhaustion method was the Platonic school's answer to Zeno Dao. It avoided the pitfalls of the infinitesimal by simply discarding them, by reducing problems which might lead to infinitesimals to problems involving formal logic only. When, for instance, it was required to prove that the volume V of a tetrahedron is equal to 1/3 the volume P of a prism of equal base and altitude, the proof consisted in showing that both the assumptions V greater than 1/3 P and V less than 1/3 P led to absurdities. For this purpose an axiom was introduced, now known as the axiom of Archimedes, and which also underlies Eudoxus' theory of proportions, namely, that magnitudes are said to have a ratio to one another which are capable, when multiplied, of exceeding one another. This method, which became the standard Greek and Renaissance mode of strict proof in area and volume computation, was quite rigorous, and can easily be translated into a proof satisfying the requirements of modern analysis. It had the great disadvantage that the result, in order to be proved, must be known in advance so that the mathematician finds it first by some other, less rigorous and more tentative method. There are clear indications that such another method was actually used. We possess a letter from Archimedes to Eratosthenes, around 250 BC, which was not discovered until 1906, in which Archimedes described a non-rigorous but fertile way of finding results. This letter is known as the method. It has been suggested, notably by S.C. Luria, that it represented a school of mathematical reasoning competing with the school of Eudoxus, also dating back to the period of the crisis, and associated with the name of Democritus, the founder of the atom theory. In Democritus' school, according to the theory of Luria, the notion of the geometrical atom was introduced. A line segment, an area or a volume was supposed to be built up of a large but finite number of indivisible atoms. The computation of a volume was the summation of the volumes of all the atoms of which this body consists. This theory sounds perhaps absurd until we realize that several mathematicians of the period before Newton, notably Vieta and Kepler, used essentially the same conceptions, taking the circumference of a circle as composed of a very large number of tiny line segments. There is no evidence that antiquity ever developed a rigorous method on this foundation. But our modern limit conceptions have made it possible to build this atom theory into a theory as rigorous as the exhaustion method. Even today we use this conception of the atoms quite regularly by setting up a mathematical problem in the theory of elasticity. In physics or in chemistry, reserving the rigorous limit theory to the professional mathematician. The advantage of the atom method over the exhaustion method was that it facilitated the finding of new results. Antiquity had thus the choice between a rigorous but relatively sterile, and a loosely founded but far more fertile method. It is instructive that in practically all the classical texts the first method was used. This again may have a connection with the fact that mathematics had become a hobby of a leisure class, basing itself on slavery, indifferent to invention, and interested in contemplation. It may also be a reflection of the victory of Platonic idealism over Democritan materialism in the realm of mathematical philosophy. In 334 BC, Alexander the Great began his conquest of Persia. When he died at Babylon in 323, the whole Near East had fallen to the Greeks. Alexander's conquests were divided among his generals, and eventually three empires emerged: Egypt under the Ptolemies, Mesopotamia and Syria under the Seleucids, and Macedonia under Antigonos and his successors. Even the Indus Valley had its Greek princes. The period of Hellenism had begun. The immediate consequence of Alexander's campaign was that the advance of Greek civilization over large sections of the Oriental world was accelerated. Egypt, Mesopotamia, and a part of India were Hellenized. The Greeks flooded the Near East as traders, merchants, physicians, adventurers, travelers, and mercenaries. The cities, many of them newly founded and recognizable by their Hellenistic names, were under Greek military and administrative control, and had a mixed population of Greeks and Orientals. But Hellenism was essentially an urban civilization. The countryside remained native and continued its existence in the traditional way. In the cities, the ancient Oriental culture met with the imported civilization of Greece and partly mixed with it, though there always remained a deep separation between the two worlds. The Hellenistic monarchs adopted Oriental manners, had to deal with Oriental problems of administration, but stimulated Greek arts, letters, and sciences. Greek mathematics, thus transplanted to new surroundings, kept many of its traditional aspects, but experienced also the influence of the problems in administration and astronomy which the Orient had to solve. This close contact of Greek science with the Orient was extremely fertile, especially during the first centuries. Practically all the really productive work which we call Greek mathematics was produced in the relatively short interval from 350 to 200 BC. From Eudoxus to Apollonius, and even Eudoxus's achievements are only known to us through their interpretation by Euclid and Archimedes. And it is also remarkable that the greatest flowering of this Hellenistic mathematics occurred in Egypt, under the Ptolemies, and not in Mesopotamia, despite the more advanced status of native mathematics in Babylonia. The reason for this development may be found in the fact that Egypt was now in a central position in the Mediterranean world. Alexandria, the new capital, was built on the seacoast and became the intellectual and economic center of the Hellenistic world. But Babylon lingered on only as a remote center of caravan roads, and eventually disappeared to be replaced by Ctesiphon Seleucia, the new capital of the Seleucids. No great Greek mathematicians, as far as we know, were ever connected with Babylon. Antioch and Pergamum, also cities of the Seleucid Empire, but closer to the Mediterranean, had important Greek schools. The development of native Babylonian astronomy and mathematics even reached its height under the Seleucids, and Greek astronomy received an impetus, the importance of which is only now beginning to be better understood. Beside Alexandria, there were some other centers of mathematical learning, especially Athens and Syracuse. Athens became an educational center, while Syracuse produced Archimedes, the greatest of Greek mathematicians. In this period, the professional scientist appeared, a man who devoted his life to the pursuit of knowledge and received a salary for doing it. Some of the most outstanding representatives of this group lived in Alexandria, where the Ptolemies built a great center of learning in the so-called museum with its famous library. Here the Greek heritage in science and literature was preserved and developed. The success of this enterprise was considerable. Among the first scholars associated with Alexandria was Euclid, one of the most influential mathematicians of all time. Euclid, about whose life nothing is known with any certainty, lived probably during the time of the first Ptolemy, around 306 to 283 BC, to whom he is supposed to have remarked that there is no royal road to geometry. His most famous and most advanced texts are the 13 books of his Elements, Stoichia, though he is also credited with several other minor texts. Among these other texts are the Data, containing what we would call applications of algebra to geometry, but presented in strictly geometrical language. We do not know how many of these texts are Euclid's own and how many are compilations, but they show at many places an astonishing penetration. They are the first full mathematical texts that have been preserved from Greek antiquity. The Elements form, next to the Bible, probably the book most reproduced and studied in the history of the Western world. More than 1,000 editions have appeared since the invention of printing, and before that time manuscript copies dominated much of the teaching of geometry. Most of our school geometry is taken, often literally, from 6 of the 13 books, and the Euclidean tradition still weighs heavily on our elementary instruction. For the professional mathematician, these books have always had an inescapable fascination, and their logical structure has influenced scientific thinking perhaps more than any other text in the world. Euclid's treatment is based on a strictly logical deduction of theorems from a set of definitions, postulates, and axioms. The first 4 books deal with plane geometry and led from the most elementary properties of lines and angles to the congruence of triangles. The equality of areas, the theorem of Pythagoras, the construction of a square equal to a given rectangle, the golden section, the circle, and the regular polygons. The 5th book presents Eudoxus' theory of incommensurables in its purely geometrical form. And in the 6th book, this is applied to the similarity of triangles. This introduction of similarity at such a late stage is one of the most important differences between Euclid's presentation of plane geometry and the present one, and must be ascribed to the emphasis laid by Euclid on Eudoxus' novel Theory of Incommensurables. The geometrical discussion is resumed in the 10th book. Often considered Euclid's most difficult one, which contains a geometrical classification of quadratic irrationals and of their quadratic roots, hence of what we call numbers of a form like the square root of a plus, the square root of b. The last 3 books deal with solid geometry and led via solid angles. The volumes of parallelepipeds, prisms, and pyramids to the sphere, and to what seems to have been intended as the climax, the discussion of the 5 regular, Platonic bodies, and the proof that only 5 such bodies exist. Books 7 to 9 are devoted to number theory, not to computational technique, but to such Pythagorean subjects as the divisibility of integers, the summation of the geometrical series, and some properties of prime numbers. There we find both Euclid's algorithm to find the greatest common divisor of a given set of numbers, and Euclid's theorem that there are an infinite number of primes. Of particular interest is Theorem 27 of Book 6, which contains the first maximum problem that has reached us, with the proof that the square of all rectangles of given perimeter has maximum area. The 5th postulate of Book 1 is equivalent to the so-called parallel axiom, according to which one and only one line can be drawn through a point parallel to a given line. Attempts to reduce this axiom to a theorem led in the 19th century to a full appreciation of Euclid's wisdom in adopting it as an axiom and to the discovery of other so-called non-Euclidean geometries. Algebraic reasoning in Euclid is cast entirely into geometrical form. An expression like the square root of a is introduced as the side of a square of area a. A product, a times b, as the area of a rectangle with sides a and b. This mode of expression was primarily due to Eudoxus' theory of proportions, which consciously rejected numerical expressions for line segments, and in this way dealt with incommensurables in a purely geometrical way, numbers being conceived only as integers or rational fractions. What was Euclid's purpose in writing his Elements? We may assume with some confidence that he wanted to bring together into one text 3 great discoveries of the recent past: Eudoxus' theory of proportions, Theaetetus' theory of irrationals, and the theory of the 5 regular bodies which occupied an outstanding place in Plato's cosmology. But these were all 3 typically Greek achievements. The greatest mathematician of the Hellenistic period, and of antiquity as a whole, was Archimedes, who lived from 287 to 212 BC, in Syracuse, as an advisor to King Hiero. He is one of the few scientific figures of antiquity who is more than a name. Several data about his life and person have been preserved. We know that he was killed when the Romans took Syracuse after he placed his technical skill at the disposal of the defenders of the city. This interest in practical application strikes us as odd if we compare it to the contempt in which such interest was held in the Platonic school of his contemporaries. But an explanation is found in the much-quoted statement in Plutarch's Marcellus. Although these inventions had obtained for him the reputation of more than human sagacity, he did not deign to leave behind any written work on such subjects, but, regarding as ignoble and sordid the business of mechanics and every sort of art which is directed to use and profit, he placed his whole ambition in those speculations, the beauty and subtlety of which are untainted by any admixture of the common needs of life. The most important contributions which Archimedes made to mathematics were in the domain of what we now call the integral calculus, theorems on areas of plane figures and on volumes of solid bodies. In his measurement of the circle, he found an approximation of the circumference of the circle by the use of inscribed and circumscribed regular polygons. Extending his approximation to polygons of 96 sides, he found that the value of pi lies between 3 plus 10^71 and 3 plus 1/7. In Archimedes' book on the sphere and cylinder, we find the expression for the area of the sphere in the form that the area of a sphere is 4 times that of a great circle, and for the volume of a sphere in the form that this volume is equal to 2/3 of the volume of the circumscribed cylinder. Archimedes' expression for the area of a parabolic segment is 4/3 the area of the inscribed triangle with the same base as the segment, and its vertex at the point where the tangent is parallel to the base. In the book on spirals, we find the spiral of Archimedes with area computations. In onoids and spheroids, we find the volumes of certain quadratic surfaces of revolution. Archimedes' name is also connected with his theorem on the loss of weight of bodies submerged in a liquid, which can be found in his book on floating bodies, a treatise on hydrostatics. In all these works, Archimedes combined a surprising originality of thought with a mastery of computational technique and rigor of demonstration. Typical of this rigor is the axiom of Archimedes already quoted, and his consistent use of the exhaustion method to prove the results of his integration. We have seen how he actually found these results in a more heuristic way, by weighing infinitesimals, but he subsequently published them in accordance with the strictest requirements of rigor. In his computational proficiency, Archimedes differed from most of the productive Greek mathematicians. This gave his work, with all its typically Greek characteristics, a touch of the Oriental. This touch is revealed in his cattle problem, a very complicated problem in indeterminate analysis which may be interpreted as a problem leading to an equation of the Pell type, x squared minus 4,729,429,494, y squared equals 1, which is solved by very large numbers. This is only one of many indications that the Platonic tradition never entirely dominated Hellenistic mathematics. Hellenistic astronomy points in the same direction. With the third great Hellenistic mathematician, Apollonius of Perga, who lived circa 260 to circa 170 BC, we are again entirely within the Greek geometrical tradition. Apollonius, who seems to have taught at Alexandria and at Pergamum, wrote a treatise of 8 books on conics, of which 7 have survived, 3 only in an Arabic translation. It is a treatise on the ellipse, parabola, and hyperbola, introduced as sections of a circular cone, and penetrates as far as the discussion of the evolutes of a conic. We know these conics by the names found in Apollonius. They refer to certain area properties of these curves, which are expressed in our notation by the equations y squared equals px, y cubed equals px plus or minus x cubed. Parabola here means application, ellipse application with deficiency, hyperbola application with excess. Apollonius did not have our coordinate method because he had no algebraic notation, probably rejecting it consciously under the influence of the school of Eudoxus. Many of his results, however, can be transcribed immediately into coordinate language, including his property of the evolutes, which is identical with the Cartesian equation. This can also be said for other books by Apollonius, of which parts have been preserved and which contain algebraic geometry in geometrical and therefore homogeneous language. Here we find Apollonius's tangency problem, which requires the construction of the circles tangent to 3 given circles. The circles may be replaced by straight lines or points. In Apollonius, we meet for the first time in explicit form the requirement that geometrical constructions be confined to compass and ruler only, which therefore was not such a general Greek requirement as is sometimes believed. Mathematics, throughout its history and until modern times, cannot be separated from astronomy. The needs of irrigation and of agriculture in general, and to a certain extent also of navigation, accorded to astronomy the first place in Oriental and in Hellenistic science, and its course determined to no small extent that of mathematics. The computational and often also the conceptual content of mathematics was largely conditioned by astronomy, and the progress of astronomy depended equally on the power of the mathematical books available. The structure of the planetary system is such that relatively simple mathematical methods allow far-reaching results, but are at the same time complicated enough to stimulate the improvement of these methods and of the astronomical theories themselves. The Orient itself had made considerable advances in computational astronomy during the period just preceding the Hellenistic era, especially in Mesopotamia during the late Assyrian and Persian periods. Here, observations consistently carried on over a long period had allowed a remarkable understanding of many ephemerides. The motion of the moon was one of the most challenging of all astronomical problems to the mathematician. In antiquity as well as in the 18th century, and Babylonian, Chaldean astronomers devoted much effort to its study. The meeting of Greek and Babylonian science during the Seleucid period brought great computational and theoretical advancement. And where Babylonian science continued in the ancient calendaric tradition, Greek science produced some of its most significant theoretical triumphs. The oldest known Greek contribution to theoretical astronomy was the planetary theory of the same Eudoxus who inspired Euclid. It was an attempt to explain the motion of the planets around the Earth by assuming the superposition of 4 rotating concentric spheres, each with its own axis of rotation with the ends fixed on the enclosing sphere. This was something new and typically Greek, an explanation rather than a chronicle of celestial phenomena. Despite its crude form, Eudoxus's theory contained the central idea of all planetary theories until the 17th century, which consisted in the explanation of irregularities in the apparent orbits of moon and planets by the superposition of circular movements. It still underlies the computational side of our modern dynamic theories as soon as we introduce Fourier series. Eudoxus was followed by Aristarchus of Samos, around 280 BC. The Copernicus of antiquity, credited by Archimedes with the hypothesis that the Sun, and not the Earth, is the center of the planetary motion. This hypothesis found few adherents in antiquity, though the belief that the Earth rotates about its axis had a wide acceptance. The small success of the heliocentric hypothesis was mainly due to the authority of Hipparchus, often considered the greatest astronomer of antiquity. Hipparchus of Nicaea made observations between 161 and 126 BC. Little of his work has come to us directly, the main source of our knowledge of his achievements coming through Ptolemy, who lived 3 centuries later. Much of the contents of Ptolemy's great work, the Almagest, may be ascribed to Hipparchus, especially the use of eccentric circles and epicycles to explain the motion of sun, moon, and planets, as well as the discovery of the precession of the equinoxes. Hipparchus is also credited with a method to determine latitude and longitude by astronomical means. But antiquity never was able to muster a scientific organization sufficient to do any large-scale mapping. Scientists in antiquity were very thinly scattered, both in locality and in time. Hipparchus's work was closely connected with the achievements of Babylonian astronomy, which reached great heights in this period. And we may see in this work the most important scientific fruit of the Greek-Oriental contact of the Hellenistic period. The third and last period of antique society is that of the Roman domination. Syracuse fell to Rome in 212 BC. Carthage in 146 BC, Greece in 146 BC, Mesopotamia in 64 BC, and Egypt in 30 BC. The whole Roman-dominated Orient, including Greece, was reduced to the status of a colony ruled by Roman administrators. This control did not affect the economic structure of the Oriental countries, as long as the heavy taxes and other levies were duly delivered. The Roman Empire naturally split into a western part with extensive agriculture fitted for wholesale slavery, and an eastern part with intensive agriculture which never used slaves, except for domestic duties and for public works. Despite the growth of some cities and a commerce embracing the whole of the known Western world, the entire economic structure of the Roman Empire remained based on agriculture. The spread of a slave economy in such a society was fatal to all original scientific work. Slave owners as a class are seldom interested in technical discoveries, partly because slaves can do all the work cheaply, and partly because they fear to give any tool into the hands of slaves which may sharpen their intelligence. Many members of the ruling class dabbled in the arts and sciences, but this very dabbling promoted mediocrity rather than productive thinking. When with the decline of the slave market Roman economy declined, there were few men to cultivate even the mediocre science of the past centuries. As long as the Roman Empire showed some stability, Eastern science continued to flourish as a curious blend of Hellenistic and Oriental elements, though originality and stimulation gradually disappeared. The Pax Romana lasting for many centuries allowed undisturbed speculation along traditional lines. Coexistent with the Pax Romana was for some centuries the Pax Sinensis. The Eurasian continent in all its history never knew such a period of uninterrupted peace as under the Antonines in Rome and the Han in China. This made the diffusion of knowledge over the continent from Rome and Athens to Mesopotamia. China and India, easier than ever before. Hellenistic science continued to flow into China and India, and was influenced in its turn by the science of those countries. Glimpses of Babylonian astronomy and Greek mathematics came to Italy, Spain and Gaul. An example is the spread of the sexagesimal division of angle and hour over the Roman Empire. There exists a theory of Waka, which traces the spread of the so-called Hindu-Arabic numerals over Europe to Neo-Pythagorean influences in the later Roman Empire. This may be true, but if the spread of these numerals goes back that far, then it is more likely due to the influences of trade rather than of philosophy. Alexandria remained the center of antique mathematics. Original work continued, though compilation and commentarization became more and more the prominent form of science. Many results of the ancient mathematicians and astronomers have been transmitted to us through the works of these compilers, and it is sometimes quite difficult to find out what they transcribed and what they discovered themselves. In trying to understand the gradual decline of Greek mathematics, we must also take its technical side into account. The clumsy geometrical mode of expression with the consistent rejection of algebraic notation, which made any advance beyond the conic sections almost impossible. Algebra and computation were left to the despised Orientals, whose lore was covered by a veneer of Greek civilization. It is wrong, however, to believe that Alexandrian mathematics was purely Greek in the traditional Euclidean Platonic sense. Computational arithmetics and algebra of an Egyptian Babylonian type were cultivated side by side with abstract geometrical demonstrations. We have only to think of Ptolemy, Heron, and Diophantus to become convinced of this fact. The only tie between the many races and schools was the common use of Greek. One of the earliest Alexandrian mathematicians of the Roman period was Nicomachus of Gerasa around 100 AD, whose arithmetic introduction is the most complete exposition extant of Pythagorean arithmetic. It deals in great part with the same subjects as the arithmetical books of Euclid's Elements. But where Euclid represents numbers by straight lines, Nicomachus uses arithmetical notation with ordinary language when undetermined numbers are expressed. His treatment of polygonal numbers and pyramidal numbers was of influence on medieval arithmetic, especially through Boethius. One of the greatest documents of this Second Alexandrian period was Ptolemy's great collection, better known under the Arabicized title of Almagest around 150 AD. The Almagest was an astronomical opus of supreme mastership and originality, even if many of the ideas may have come from Hipparchus or Kidinu and other Babylonian astronomers. It also contained a trigonometry, with a table of chords belonging to different angles, equivalent to a sine table of angles ranging from 0 degrees to 90 degrees, ascending by halves of an angle. Ptolemy found for the chord of 1 degree the value 1 2/50. The correct value is 0.017453. For pi, the value 3, 1/8 and 1/530 equals 3.14616. We find in the Almagest the formula for the sine and cosine of the sum and difference of two angles, together with the beginning of spherical trigonometry. The theorems were expressed in geometrical form. We also meet in this book Ptolemy's theorem for a quadrilateral, inscribed in a circle. In Ptolemy's Planispherium, we find a discussion of stereographic projection and of latitude and longitude in a sphere, which are ancient examples of coordinates. Somewhat older than Ptolemy was Menelaus around 100 AD, whose Spherica contained a geometry of the sphere with a discussion of spherical triangles, a subject which is missing in Euclid. Here we find Menelaus' theorem for the triangle in its extension to the sphere. Where Ptolemy's astronomy contained a good deal of computational work in sexagesimal fractions, Menelaus's treatise was geometrical in the pure Euclidean tradition. To the period of Menelaus may also belong Heron. At any rate, we know that he described accurately a lunar eclipse of 62 AD. Heron was an encyclopedic writer who wrote on geometrical, computational, and mechanical subjects. They show a curious blend of the Greek and Oriental. In his Metrica, he derived the Heronic formula for the area of a triangle, the square root of s times the quantity s minus a times the quantity s minus b times the quantity s minus c, in purely geometrical form. The proposition itself has been ascribed to Archimedes. In the same Metrica, we find typical Egyptian unit fractions, as in the approximation of the square root of 63 by 7 plus 1 4 plus 1 8 plus 1 16. Heron's formula for the volume of a frustum of a square pyramid can readily be reduced to the one found in the ancient Moscow papyrus. His measurement of the volume of the 5 regular polyhedra, not, on the contrary, was again in the spirit of Euclid. The Oriental touch is even stronger in the Arithmetica of Diophantus, around 250 AD. Only 6 of the original books survive. Their total number is a matter of conjecture. Their skillful treatment of indeterminate equations shows that the ancient algebra of Babylon, or perhaps India, not only survived under the veneer of Greek civilization, but also was improved by a few active men. How and when it was done is not known. Just as we do not know who Diophantus was, he may have been a Hellenized Babylonian. His book is one of the most fascinating treatises preserved from Greek-Roman antiquity. Diophantus's collection of problems is of wide variation, and their solution is often highly ingenious. Diophantine analysis consists in finding answers to such indeterminate equations as x squared plus b, x plus c, equals y squared, x cubed plus b x cubed plus cx plus d equals y cubed, or sets of these equations. Typical of Diophantus is that he was only interested in positive rational solutions. He called irrational solutions impossible, and was careful to select his coefficients so as to get the positive rational solution he was looking for. Among the equations, we find x squared minus 26y cubed equals 1, x squared minus 3y cubed equals 1, now known as Pell equations. Diophantus also has several propositions in the theory of numbers, such as the theorem that if each of 2 integers is the sum of 2 squares, their product can be resolved in 2 ways into 2 squares. There are theorems about the division of a number into the sum of 3 and 4 squares. In Diophantus we find the first systematic use of algebraic symbols. He has a special sign for the unknown, for the minus, for reciprocals. The signs are still of the nature of abbreviations rather than algebraic symbols in our sense. For each power of the unknown there exists a special symbol. There is no doubt that we have here not only, as in Babylon, arithmetical questions of a definite algebraic nature, but also a well-developed algebraic notation, which was greatly conducive to the solution of problems of greater complication than were ever taken up before. The last of the great Alexandrian mathematical treatises was written by Pappus around the end of the 3rd century. His collection, Synagogue, was a kind of handbook to the study of Greek geometry with historical annotations, improvements, and alterations of existing theorems and demonstrations. It was to be read with the original works rather than independently. Many results of ancient authors are known only in the form in which Pappus preserved them. Examples are the problems dealing with the quadrature of the circle, the duplication of the cube, and the trisection of the angle. Interesting is his chapter on isoperimetric figures, in which we find the circle has a larger area than any regular polygon of equal perimeter. Here is also the remark that the cells in the honeycomb satisfy certain maximum-minimum properties. Archimedes' semi-regular solids are also known through Pappus. Like Diophantus's Arithmetica, the collection is a challenging book whose problems inspired much further research in later days. The Alexandrian school gradually died with the decline of antique society. It remained, as a whole, a bulwark of paganism against the progress of Christianity, and several of its mathematicians have also left their mark on the history of ancient philosophy. Proclus, who lived from 410 to 485, whose commentary on the first book of Euclid is one of our main sources of the history of Greek mathematics, headed a Neoplatonist school in Athens. Another representative of this school in Alexandria was Hypatia, who wrote commentaries on the classical mathematicians. She was murdered in 415 by the followers of Saint Cyril, a fate which inspired a novel by Charles Kingsley. These philosophical schools with their commentators had their ups and downs for centuries. The academy in Athens was discontinued as pagan by the Emperor Justinian in 529, but by this time there were again schools in such places as Constantinople and Jundashapur. Many old codices survived in Constantinople, while commentators continued to perpetuate the memory of Greek science and philosophy in the Greek language. In 630, Alexandria was taken by the Arabs, who replaced the upper layer of Greek civilization in Egypt by an upper layer of Arabic. There is no reason to believe that the Arabs destroyed the famous Alexandrian library, since it is doubtful whether this library still existed at that time. As a matter of fact, the Arabic conquests did not materially change the character of the mathematical studies in Egypt. There may have been a retrogression. But when we hear of Egyptian mathematics again, it is still following the ancient Greek Oriental tradition. We end this chapter with some remarks on Greek arithmetic and logistics. Greek mathematicians made a difference between arithmetica, or science of numbers, and logistics, or practical computation. The term arithmos expressed only a natural number, a quantity composed of units. This also meant that one was not considered a number. Our conception of a real number was unknown. A line segment, therefore, had not always a length. Geometrical reasoning replaced our work with real numbers. When Euclid wanted to express that the area of a triangle is equal to half base times altitude, he had to state that it is half the area of a parallelogram of the same base and line between the same parallels. Pythagoras' theorem was a relation between the areas of three squares and not between the lengths of three sides. This conception must be considered as a deliberate act brought about by the victory of Platonic idealism among those sections of the Greek ruling class interested in mathematics, since the contemporary Oriental conceptions concerning the relation of algebra and geometry did not admit any restriction of the number concept. There is every reason to believe that. For the Babylonians, Pythagoras' theorem was a numerical relation between the lengths of sides, and it was this type of mathematics with which the Ionian mathematicians had become acquainted. Ordinary computational mathematics, known as logistics, remained very much alive during all periods of Greek history. Euclid rejected it, but Archimedes and Heron used it with ease and without scruples. Actually, it was based on a system of numeration which changed with the times. The early Greek method of numeration was based on an additive decimal principle like that of the Egyptians and the Romans. In Alexandrian times, perhaps earlier, a method of writing numbers appeared which was used for 15 centuries, not only by scientists but also by merchants and administrators. It used the successive symbols of the Greek alphabet to express. First our symbols 1 through 9, then the tens from 10 to 90, and finally the hundreds from 100 to 900. 3 extra archaic letters were added to the 24 letters of the Greek alphabet, in order to obtain the necessary 27 symbols. With the aid of this system, every number less than 1000 could be written with at most 3 symbols. For example, 14 is I delta, since iota equals 10, delta equals 4. Numbers larger than 1000 could be expressed by a simple extension of the system. It is used in the existing manuscripts of Archimedes, Heron, and all the other classical authors. There is archaeological proof that it was taught in the schools. This was a decimal non-position system. Both I delta and delta I could only mean 14. This lack of place value and the use of no less than 27 symbols have occasionally been taken as a proof of the inferiority of the system. The ease with which the ancient mathematicians used it, its acceptance by Greek merchants even in rather complicated transactions, and its long persistence in the East Roman Empire until its very end in 1453, seem to point to certain advantages. Some practice with the system can indeed convince us that it is possible to perform the 4 elementary operations easily enough once the meaning of the symbols is mastered. Fractional calculus with a proper notation is also simple. But the Greeks were inconsistent because of their lack of a uniform system. They used Egyptian unit fractions, Babylonian sexagesimal fractions, and also fractions in a notation reminiscent of ours. Decimal fractions were never introduced, but this great improvement appears only late in the European Renaissance, after the computational apparatus had extended far beyond anything ever used in antiquity. Even then, decimal fractions were not adopted in many schoolbooks until the 18th and 19th centuries. It has been argued that this alphabetical system has been detrimental to the growth of Greek algebra, since the use of letters for definite numbers prevented their use for denoting numbers in general, as we do in our algebra. Such a formal explanation of the absence of a Greek algebra before Diophantus must be rejected, even if we accept the great value of an appropriate notation. If the classical authors had been interested in algebra, that-wise, they would have created the appropriate symbolism with which Diophantus actually made a beginning. The problem of Greek algebra can be elucidated only by further study of the connections between Greek mathematicians and Babylonian algebra in the framework of the entire relationship of Greece and the Orient.